Hello, I'm Niluthpol Mithun, a computer vision scientist at SRI International in Princeton, New Jersey. I'll be presenting our WCV 2024 work, Unsupervised Domain Adaptation for Semantic Segmentation with Pseudo-label Self-Refinement. As the name suggests, we are interested in unsupervised domain adaptive semantic segmentation. That means that we would like to adopt a segmentation model trained from label source data to an unlabeled target domain. For example, many labeled outdoor daytime driving datasets are available like cityscape, but for our target domain like nighttime driving, there may be only unlabeled data available. And a model trained on a daytime domain will generally perform poorly on the nighttime domain. So unsupervised domain adaptation for semantic segmentation methods focus on addressing this problem. And this is an important problem because in semantic segmentation, the labeling is quite costly because we need a per pixel annotation. And again, labeling all the target images is difficult. So there have been recently a lot of interest. And as we see in the literature that most of the state-of-the-art prior works are based on self-training. So here we have a typical self-training unsupervised domain adaptation method in the figure. So what happens is that we have a label source image domain and the target domain with which is unlabeled. So there is a teacher model that provides pseudo-label for the target domain. And this teacher model is updated using an exponential moving average of the student model after each iteration. So this allows teacher to provide a stable pseudo-label prediction over time. So now the student model is trained with the pseudo-label predicted by teacher and the source ground truth label. Using this with the source loss and target loss, the student model is trained, which is our final model. So here in this process, you can see the main problem is coming from the inherent noise coming from the pseudo-label noise due to the source target domain gap. And these noisy labels can degrade performance significantly over the training. Now, our proposed method is also based on self-training. And to improve the pseudo-label quality, we propose an auxiliary label refinement network. Let's see that in more detail. So we propose a pseudo-label refinement network, which is shown in gray in the figure. Now see the top part of the figure is similar to the standard self-training pipeline. Our idea is to introduce this additional auxiliary pseudo-label refinement network that can perform two tasks. The first task focuses on refining pseudo-label. The second task focuses on pseudo-label selection. Means it provides a binary mask which shows that which part of the label may be noisy, which is not. It is just possible to use this one task, just refine pseudo-label, target pseudo-label generation to use, but we found that doing both helps. And because this noise mask prediction, which is binary task, this is a class agnostic task compared to the refining pseudo-label, which is a class specific task. So this class agnostic task is easier and performs better in providing the noise. And when we reweight the target loss using this both binary mask, that helps us improve the performance. Now the question is, how do we train this pseudo-label refinement network? We need to train it somehow. And what type of ground truth label we have for that? So the label refinement network training, we develop a Fourier transform-based strategy. Let's discuss it. So what we can do is that for using Fourier transform, any data we can divide into two components, phase and amplitude. So in general, we have seen in image data, phase encodes semantic information like the object structure, and amplitude encodes style information. So for perturbing source logic, we keep the phase same and we perturb the amplitude with some factor from target random targets segmentation logic. So that gives us a perturbed source image that also have some information about target and target style, while preserving the object structure of the source image. That helps us use the ground truth label for the source data as supervision, while the style information for the target domain also acts as training input for the perturbed logics. And now based on the difference, we can get the noise binary mask ground truth between perturbed and unperturbed one. And within inverse FFT, we can get again the segmentation logic spec. We can perturb target segmentation logic just in the opposite way, based on taking a factor of amplitude from source segmentation logics. And in that case, we take, because we don't have ground truth label, we take the pseudo-label predicted from unperturbed target segmentation logics as ground truth. So here we train in the pseudo-label refinement network, we take perturbed segmentation logics, source image feature, and we want to predict refined pseudo-label and noise mask. That's we train with 2 cross entropy losses. So along with this pseudo-label refinement network, we have 2 additional components in our method. That's one is we use a style transform technique to change the input source image to the target style. We can use any style transform technique here, like a GAN-based method, and we used a simple Fourier adaptation method there. We also use contrastive learning to further stabilize the training. That's used to reduce the distance in positive pairs coming from same object class and increase the distance in negative pairs coming from different object class. Now let's come to experiment. We experiment in 3 benchmarks, 2 synthetic to real and 1 day to night adaptation benchmark. In synthetic to real, we have GTA to cityscape here and Cynthia to cityscape here. We compare, we use default backbone, we use a ResNet-based backbone lab version 2 based on prior work. We have results here and we have a transformized segformer backbone here. So we see that using any backbone like ResNet-based backbone, we perform better than state of the art. Also using a segformer-based backbone, we perform better than prior works like DA-former MIC, and with a high resolution training, we perform achieve even further improvement. An ablation study shown in the table below. There are different components of the methods like using self-training, pseudo-label refinement, noise mask, contrastive learning style transform. We see that all of the components continue to consistently improve our performance. Now we have the result on daytime to nighttime adaptation. We perform this experiment on cityscape to Chowdhury. So we can see again, we use ResNet-based backbone and also perform experiment with segformer-based backbone. Here is one important thing to say that there are several existing day-to-night adaptation methods that use paired images as auxiliary data. They consider that from the target domain, although they don't have label, but they have the images collected from the same place at different time. So that helps them reduce the domain gap. We don't use that, but still we can see that our method achieves 58.4 compared to the prior best one refine, that's 56.2. That also is a paired image and still perform significantly better. And in ablation study, again, we see that as we continue to add different components to our method, our performance consistently improves. Now, let's see some qualitative results. Here are 2 examples. These examples are to analyze the quality of noise mask prediction from our pseudo-label refinement module. So you can see that this is the input target image on the left, then the middle original target model prediction, and the predicted noise mask on the right. We can see that the noise mask generally correspond well to the noisy part of the pseudo-labels in both the cases. Next, here are some qualitative examples, semantic map from our method comparing source-only DA-former and proposed. We can see on all the examples in both day to night and synthetic to real adaptation, our method performs much better than the baselines. To conclude, we propose training an auxiliary pseudo-label refinement network to help self-training to be less susceptible to erroneous pseudo-label predictions. We develop a novel strategy using FFT-based perturbation to train that module, and our method outperforms state-of-the-art methods in several segmentation benchmarks with significant margin. Thank you very much for listening.